Okay, in our last video, we're going to talk about what's called induced transmutation, which means the process of striking nuclei with high velocity charged particles. So we're basically going to be making one element turn into another element. They do this on their own if they're radioactive, but sometimes we can force that to happen by bombarding a particular isotope with either alpha, beta, gamma radiation, or some other high energy particles. So as you can see here, we have nitrogen 14, and we want to make it turn into oxygen. So we're going to bombard it with an alpha particle. Now, if you notice, when we pay attention to our mass numbers and atomic numbers, when we look at what we're making here, then we have 4 plus 14 is 18. So if we're making 17, then it gives off a hydrogen atom. 17 plus 1 is 18. Then if we look at the bottom, 2 plus 7 is 9. 8 plus 1 is 9. So we balance out with our nuclear equation. All right, now the transuranium elements, just like that word means, transuranium means after uranium, and they're elements with atomic number 93 and higher. They are all man-made elements. They were made using induced transmutation. That's how those elements were made, how they're discovered, and where they come from in a lab is by using this particular process. Okay, so let's look at an example. Here we go. We have write a balanced nuclear equation for the induced transmutation of oxygen-16 into nitrogen-13 by proton bombardment. An alpha particle is emitted from the nitrogen atom in the reaction. All right, so let's think about what are we starting with? Well, we are changing oxygen into nitrogen. So we're going to start with oxygen-16. So we have our 16 and our oxygen, and we know that oxygen is element number 8, so that's our atomic number, and we're going to bombard it with a proton. Now, here's how we write a proton. Proton is 1, 1 with a P. Okay, it has a charge of 1 and a mass of 1, so that's where those 1s come from. And then we know that an alpha particle is emitted, and we know an alpha particle is 4, 2, He. And we want to figure out what this nitrogen looks like. So 16 plus 1 is 17, 4 plus 13 is 17, and it tells us it's nitrogen 13. 8 plus 1 is 9, 2 plus 7 is 9, and we know element 7 is nitrogen. So it all works out when we balance our nuclear equation. All right, now, when is induced transmutation useful? Why would we want to use it? Well, we want to use it in a process called nuclear fission. And nuclear fission is how you can produce a whole lot of energy using these radioactive materials. And so fission is the process of splitting a nucleus into fragments. Your fission means splitting. And fission is accompanied by a very large release of energy. So it's what's used in nuclear power plants to make energy. It's also what's used in nuclear bombs to produce energy. It all just depends on how the process is controlled. So as you can see here, a neutron strikes a uranium atom. It makes it even more unstable than it already is, and then the uranium splits into 2 new isotopes, 3 neutrons, and a whole bunch of energy. Now, what happens to these products? Well, those 3 neutrons that are produced, they can go on and strike other uranium that's going to produce more neutrons, that strikes more uranium, and we end up with what's called a chain reaction. And the chain reaction will go uncontrolled and it will happen all at once, which is what happens in a nuclear bomb, or if you can slow it down and control it and just give off a little bit of energy at a time, then you can actually produce useful energy, which is what happens in a nuclear power plant. So that's kind of how the process works, and that's what we're going to be talking about in class, is how that nuclear reactor is set up, and you have a picture of it in your notes. and I have a picture of it right here that we're going to focus on in class to really show what's going on with the fission in that nuclear power plant and how they're using it to produce energy. Okay, so we'll come back to nuclear reactors and talk more about those in class. Now, the last thing we want to look at is one more process that's called nuclear fusion. And it's kind of the opposite of fission. Fusion means bringing things together. So nuclear fusion is the combining of atomic nuclei, and it also produces a large amount of energy. Now, the good thing about fusion is you're actually putting together really light elements, things like hydrogen and helium and things that are not radioactive, which is useful because then you're not worried about the byproducts of being radioactive. The lightweight isotopes that you need are really abundant, and that's actually how the sun produces energy, is through nuclear fusion. The problem, however, is that it requires extremely high temperatures to start the process and to initiate it. So it's not something that we as the general public have figured out how to use to harness energy. But if you've ever heard of something called cold fusion, it's the idea that if you could do fusion at a lower temperature where it could be initiated and sustained, then it would produce very inexpensive, very clean energy compared to what we're using right now to produce energy. It's just not something that's actually been figured out how to do yet. So, cold fusion is the thing of the future. It's not really done yet, but we will be talking about fission and those nuclear reactors and how they work in class. Make sure you look at those radioactive Boy Scout questions and see if you can come up with some answers and bring those to class as well. We will include those in our class discussion.